Okay, thank you. Thank you very much. I'd like to thank Michel for all the organization he has been preparing and doing for us. Okay, so it's the last talk, and I promised yesterday at the restaurant it will be very relaxed, so I think it will be like that. So let me tell you a few things about several types of quantum walks, open quantum walks, unitary quantum walks, and something, as I said, in between, for which we don't have a name for a moment. We're looking for a name. Okay, so let me start with open quantum walks. So it's really an introductory presentation. Sorry for those who know that very well. So it was something we developed in a paper in 2012 with Francesco Petruccione, Ilya Sinaisky, and Christophe Szabó. So these two guys, maybe you know, they are physicists, theoretical physicists from South Africa in Durban, and myself and Christophe Szabó, we are mathematicians in Lyon. Okay, so here is the idea. The context is the following. You are given a graph or a net, so a set of vertices or a net, okay, and you consider the state space, I will call K, which is C to the power V, so Hilbert space indexed by the vertices. I will give an orthonormal basis indexed by the vertices, I. This is where we are going to walk. And we are given another Hilbert space, which is the coin space, which gives the degrees of freedom for our coin, for the walk. So everything I'm talking about is happening on this space, H tensor K. We are given the following objects. Operators, let's say matrices. Let's say H is finite dimensional. I don't want to. It can be infinite dimensional. There is no problem. But okay, for the talk, let's say we have matrices. Okay, so operators on H, Bij, they stand for the effect when you go from I to J. Okay? And we ask something, a condition, which is this one, for every, so Bij, for every I, the sum over J of Bij star or dagger, physicists are majority, I should maybe put a dagger, but sometimes we'll forget it and write the star as a mathematician, is the identity. So you can think of it like the condition of the transition probabilities for a Markov process, a Markov chain, but the sum of probabilities to exit is 1. Okay. So here, the sum of probabilities to exit I is 1. Okay, so define this operator, Lij, which expressed my idea, is Bij tensor Ji. Okay, so when you, on the graph, you go from site I to J, on H you have this effect. Okay, so with these conditions, I ask on Bij, you have that the sum of Lij, of Ij, of Lij, dagger Lij, is the identity. So, if you consider density matrices on H tensor K, you have a quantum channel, L of rho, which is defined like this. Which acts on density matrices on this base. Okay, it's a quantum channel. And gives you another density matrix. Okay, it's very easy to see that L of rho and all the iteration of L of rho lies in the set of density matrices which are diagonal in position, which are this form. Okay, after one application of L, you live in this set of density matrices. And so we can restrict to that, okay? And you have explicit formulas like what is L of rho in this case. It's like for a Markov chains. It looks like the same. You will have L of rho to be of the same form. But what is the density matrix in position I? Is the sum of all contribution from somewhere else, which have been brought from J to I. Okay? Like for a Markov chain, same kind of things. Okay, so when you are here, you can measure the position. So you will get I with a certain probability, which is trace of this sum, right? Okay, so you have a distribution in position after one step, and you can iterate, okay? You can look at L square of rho and measure, etc. And look at the distribution. Clearly, if you write formulas, clearly, if you just look at one step, you start with a density matrix, you look at the distribution after one step, it will never help you to know the distribution after the second step, right? Because for the second step, you will have some trace of a double sum of Pij's, Bjk's, things like that, which are in no way related to that by a classical Markov chain or whatever classical process. It's really purely quantum. If you want to know your work, you really need all the ingredients, the density matrix, everything. Okay, that's what we call open quantum work. So let me show you a few things about them. First, few simulations. Okay, so what happens with the distribution in this case? It starts a bit, it depends on the examples, of course. There are plenty of examples. Oh, let me show you, before I give examples, let me show you. It's very easy and very tempting. Qu'est-ce que t'as comme? To start and study an example very quickly, because, okay, if you want to do it on a graph, even in the simplest graph, your work, you need to be given 4 matrices, right, with just this relation. Oh, dagger, sorry. I might forget it time to time. If you are given 4 matrices with this relation, you can start. you have your random walk on this very simple graph, and look what is happening, how is the density matrix evolving, what is the limit distribution, everything. If you want to look at a walk on Z, well, you can think of the simplest one, a walk to the nearest neighbors, uniform. So you just need two matrices, B and C, satisfying this. And you can start playing. Even 2 by 2 matrices, and you can start playing and look at what's happening, right? So on graphs, I don't have much things to say. There are nice things happening, but I mean, like classical Markov chains, you can have, for example, all the mass going to one point or being transported. I will show you one example. On Z or ZD, the point is that it starts sometime a bit rough, like this. You have a distribution. That's the beginning of one example. So it's not centered, not symmetric, for example, here. But after time, it becomes more and more smooth and ends up to a Gaussian. And every example we've done in Z, ZT, always ends up with Gaussians. There can be one Gaussian or several Gaussians which are moving. At the beginning, it's a bit of a mess, but with time, it always ends up in Gaussians. Even though each step is quantum, but it seems it's less and less quantum, right? That's the distribution that you compute. Okay, in my example, I take something like that. I always start with a density matrix which is centered in 0. Just, I wanted to do that. And a compute step after step, the ln of rho, and the distribution which is associated. That is a probability to find it here, here, or here. So you get this distribution, and with time, sometimes it's, as I said, unsymmetric, uncentered, moving in a direction, but after some time, it seems that something is catching him back and say, okay, you have to smoothen and come back to Gaussian behavior, which is apparently the effect of dissipation here. Let me show you. So in Z square, you get typical Gaussian distribution. You can have distributions like this. So it starts like this, which is a bit strange with a peak, and it will move, and when it moves, you'll see Gaussians appearing, and also a Dirac mass, which I consider to be a special case of Gaussian. So with time, it evolves, and you see a first Gaussian appearing, and the second one, which is going to appear. And gives you that, two Gaussians moving, spreading, plus a Dirac mass. We have plenty of examples like that. Okay. About graphs, I just want to show you, you won't see much with my simulations. It's a graph which was a line, and an example where we've made where you put your state on one side of a chain, you let it evolve, and it will be transported along the chain in order to finish at the end of the chain. So it's transported like this. And it's pushed on the right side like this. Okay. Okay, so a mathematical parenthesis about that. What are we able to prove mathematically, in particular about this central limit theorem? So we did something. You'll see my talk is mainly about these works, but you will see it's mainly about open problems. So we have proved the central limit theorem that was with Nadine Guillotin and Christophe Sabot. In the case of only one Gaussian at the limit. Only. We've been able to do that, only that. There's a proof, mathematical proof, rigorous, not that easy, but we are completely unable to prove anything in those cases where there are several Gaussians. So it's about the nearest neighbor walk, open quantum walk on ZT. So you're given operators, let's say, for example, like this, with a correct relation, which is the sum of n dagger n plus e star n, etc. is identity. Let's go. It will always give a Gaussian limit distribution. In the case where there is one Gaussian, which is connected to the following thing. You have a small CP map on H alone, which is this one. Let's take this example. Plus etc., right? You do that with 4 terms. This is a quantum channel also. And it has invariant states. The question is, well, the point is the number of Gaussians seems to be related to the structure of the set of invariant states. When there is a unique invariant state, which is not an invariant state for the main quantum channel, it's another object. When there is one invariant state, there will be one Gaussian. When there are several, there are several. When the set of invariant states is more complicated, it's a convex set like this, it's connected to the number of, apparently, number of extremal points. That will be the number of Gaussians, etc. But this we are absolutely unable to prove. Okay. What shall I say? Okay, so what has been done with these works? Let me tell you a few words and properties of these open quantum works. They contain all classical Markov chains. It's really an extension, a non-commutative extension of classical Markov chains. If you put the BIJs to be a square root of transition probabilities times unitary operators, the open quantum walk is classical. And it's a Markov chain with the transition probabilities Bij. So it really covers all contains all the classical ones. It admits an approach. It's a very good point with this work. It allows to be simulated with quantum trajectories. You can start with a state, density matrix, let it evolve one step, measure the position. So your state is now going to be reduced to one position. Start again, measure, start again, measure. It gives you the same probability as if you've been leaving it evolve for n step and measuring. Okay, which is not the case with the so-called unitary quantum walks, the usual quantum walks, all of you know. I will say a word about after. So this is very powerful. In particular, this has been a powerful tool for proving this, because you can see these quantum walks as a classical walk, kind of, in a random media, because you are walking, you have a density matrix on your pocket, and you are at a site, and the quantum trajectories tells you, okay, your density matrix will tell you where you can jump, with which probability, okay? And when you jump, it is modified. And you have a new density matrix, which will tell you extra where to go. So using tools of that classical probabilists know very well of random walks in random media, we've been able to do that. And there is a bunch of papers by Bauer, Bernard, and Tillois, also related to all this. In particular, they define an open quantum Brownian motion, so a scaling limit of this walk in continuous time and continuous space. So it's really the Brownian motion limit of this, a very, very interesting object, which were related to something we've seen in a talk this morning, the talk of Jürgen, the behavior of what they call spikes, when you have this scheme of quantum jumps, and before quantum jumps you have kind of attempts of jumping, etc. They have described this very in a very fine way with open quantum walks and continuous limits. You have a nice series of work by Carbone and Potra, where they have developed kind of all the tools that you all know with classical Markov chain, irreducibility, recurrence, transience, all this very nice characterization we have. They did it for open quantum walk. Irreducibility, recurrence, transience. And also I'd like to mention a work by Clément Pellegrini, who was here until yesterday. It's a continuous time limit also of open quantum walks, but not in space, just in time. So it's still on a graph or a net, but in time. And he has shown a nice relation with so-called generalized Limblad equations in the sense of Hans-Peter Breuer, who has made a lot of work on that. We recover that quite nicely. He recovers that quite nicely when taking a continuous time limit of open quantum walks. Okay. Okay, so that's it for open quantum walks. Okay, so keep in mind this condition. Now, let me go to unitary quantum walks. So unitary quantum walks is the word, the name I give to the usual quantum walks that you all know, Hadamard quantum walks, etc. So let me present them maybe in a way which is not usual to you, but which is the same thing actually. So same structure, BIJs, etc. But I ask, so unitary quantum walks. I ask a stronger condition for every I prime in the set of vertices. I want sum of a j, bij dagger, B I prime j equal delta I prime identity. Stronger. Of course, contains this one, okay? That's much stronger. For example, in the walk on Z, with operators B and C, we saw that for open quantum walks, you need this condition. For unitary quantum walks, you can work with that and see that you just need another condition which is this one. Okay, so you can find matrices like that, and you can start. So now, once you have this condition, you still define, well, so the Lij's, as I said, and you put L to be the sum of the Lij's. And with this condition, work a bit, L is unitary. And you define L of rho to be the associated unitary evolution. Okay, and you do the same. Evolve, measure the position, or evolve 7 steps, measure the position, and see the distribution. Believe me, this is, even if you don't recognize your babies, it's really the typical Adamar walk that you get. Let me show you a simulation. So what I show you is I start with distribution in 0 and evolve with time the distribution. Okay. I should not do. Let me do it like this. Is it okay? Yeah. So here you see the distribution with time. And you recognize, for those who have seen that before, the typical shape of the limit distribution of quantum walks, unitary quantum walks, the so-called Adamar. Yes?
What is being plotted?
It's the distribution you obtain with time, the probability of presence. So your density matrix, when you apply this, changes, okay? Let's say at step 100, so you have a density matrix which will look like this, rho 100. It will have a sum of components, rho n m, tensor, something like that. And you measure the position. Okay, so you have a certain probability to be in position I. Okay, and that's the distribution. And with time, it gives this shape for those who have already seen quantum walks like Julia Kempe has been working on for years, etc. This is a typical shape you get. A shape like this, okay? So you have a high probability to be found far away. And it's interesting to note that the spreading is proportional to n in this case, to a number of steps, right? Whereas in the quotient case, it's proportional to square root of n, the typical spreading. Okay, so in this case, it's proportional to n with a high probability to be far away, which has been used by guys to accelerate algorithms or things I don't know, I do not master. Okay, so that's what you get. Okay? These are unitary quantum walks. So now the in-between. So I will ask for your help for many things because, okay, we have an idea which is, I think is interesting, but we know absolutely nothing about these objects. Nothing, nothing, nothing. We are able to prove nothing, absolutely nothing. So you have your set of vertices or your net, and you are going to divide in blocks. Your vertices you're going to make to show the partition. Okay, so you have blocks B1, BK, say, okay? You have your graph, and you have chosen a partition in blocks. Okay. You have the same operators, Bij's, etc. You put Lij's, as I said, and you define the operator transition from block I to block J to be the sum of all contributions which goes from block I to block J of my previous operators. I group my Bij's this way. Okay, I want to see, I want to create interferences in position locally inside the blocks. So I want to define this and to define the associated quantum channel L of rho, sum over Ij, L Bi Bj, rho, L Bi Bj dagger. But it needs to be a quantum channel, and for this you need a condition. And the condition is the following. For every I prime in the same block, sum over J, Bij dagger, Bi prime J equal delta I prime identity. If you ask this condition on the Bij's, this is a quantum channel. So you see this condition, if you relate it to the two conditions I gave for the two cases here, you see that actually, so you have this intermediate quantum walk, don't know how to call them, but you have two extreme cases. Open quantum walks is when the blocks are the points. Unitary quantum walks is when you have only one block, which is all the set of vertices. And in between, you have something. You have several, all sorts of walks. And the condition here is more and more restrictive if your blocks are increasing in size. So, for example, if you choose the most restrictive condition, you can do a so-called kind of coarse graining. That is, you can move the size of the blocks with the same operators. You can have a walk like in Z. If you take this condition, which is the most restrictive of all, then you can just change the size of your blocks, and you should go from the unitary random walk to the open random walk. And what's happening in between? That's what we've been looking at. And let me show you. Okay. So I've shown you, in this case, which I call a one block, which was the Adamar case. So there was only one block, which was everyone in a single block, which was the unitary quantum walk case. Okay. If I take kind of extreme case, where there are very, very small blocks or even almost points, you should see a distribution which is the one of an open quantum walk, that is Gaussian, right, at the end. But let's see what's happening in between. That's quite interesting. 2 blocks, I think it's not very interesting. Let's go. It looks like a bit Adama, but it's not. But so you have these 2 blocks, which. So you see, the idea is in what I'm going to show you, the different examples. You have blocks. Inside of each block, you have an evolution which is almost unitary, and they communicate with each other just by the frontier. They have a small communication because you can just jump to the nearest neighbor. And you will see that if you multiply the blocks, they all unitary evolve, but collectively, we are going to take this Gaussian shape.
Where is the frontier?
I think it's here. It's the two half lines. So it seems you have a kind of Adama which is symmetrized or something. I mean, I'm a mathematician. I'm paid to prove theorems. I can say that here there is not a single thing I'm saying I'm able to prove. We know nothing. With the simplest example we've tried, we are stuck, completely stuck. We know nothing about the limit distribution. We know nothing. Let me show you our example. So let's go to 10 blocks. Maybe more interesting. So you start from 0. Okay, so you see the Adama thing. So now you go from, so it's spreading, so it meets the blocks, so the things are really starting. So you see a kind of big mess. It will be more organized later, but in each block, what you see is a kind of attempt to make an Adama shape like this. I will call it Adama shape like this. Huh? You have a kind of thing like that in each block. And in the middle, it goes a bit weird. Okay, so with 10 blocks, we get something like that. Quite difficult, but it oscillates. A bit Gaussian seen from very far away. But that's it. Okay, so it's going to become more interesting, I think, here. 25 blocks. So starts. Okay, so you see, let me go a bit further. So you see, you have globally something which starts to be a bit Gaussian, and on each block you have a kind of Adama, which is going to do something I'm going to describe later on. But you have always this shape of, we called with Francesco and Ilya a Christmas tree. It's really a Christmas tree we get. So very quickly, you will get a shape like this, but with small Adamas distribution like this. Okay. But collectively, they organize in a Gaussian. And you see, I'll show you the movie again. If you look at one Adama, one of them, so let me describe the whole process, because it's very funny. We always get the same process. I must say one thing is that simulations for this are very difficult to obtain. It takes a long time. Because you have, if you think about it, you have huge matrices to manipulate. So we have many open questions, and in particular, we are stuck by the fact that we cannot go very far for the simulation. But so a first step, I would say, you will see in my examples, is the organization of the Adama walks as a Christmas tree. Then the Christmas tree will stabilize, and you will see each of the Adama walk are going to oscillate inside their position. Let me show you again the movie. You'll see each of them here. Once they are stabilized, we are going to oscillate, staying more or less in the same place. So how do I? Yeah. Okay, so it's a mess. Then the Christmas tree starts. Not yet stabilized, but okay, it's almost stabilized. And now if you concentrate on one Adama walk, you see it oscillates. It goes like this, like this, like this, like this. It's always the case. Blocks. So organized. But it's not what is happening. There are more steps after that. So here they oscillate. And if you go further, here you will not see that. But believe me, with here you see. Now it is stopping. It's not oscillating, or less and less. So there will be another step. So Christmas tree oscillation, where they stabilize. Okay, so you think, wow, okay, we have a distribution, limit distribution. No, there's a fourth step, which I don't think you will, I'm not sure you will see in my simulation. So it's stabilized, and the distribution here, they start turning around the other direction, like this, starting from the top to the bottom. I swear, it's like that, really. I don't know. Yeah, that's the maximum we've been able to do. Yeah. So we have plenty of questions. So it seems that there are, I don't know if I should call that phase transitions. I don't know if I'm allowed to say that. I'm in a dangerous room to say that. Okay, so here you have many blocks. So you see, now the small Adamas are very small, and more or less you've gone to a pure Gaussian, etc. So here is what we have obtained with these intermediate quantum walks. Notice also one thing about the spreading. So the extreme case Adama, the spreading is proportional to n. The other extreme case open, the square root of n. And in between, it must be a formula about the typical spreading, which depends on n and the size of the blocks. Which there's something, it must be between n and square root of n. And go, you see it's more, you could see in my, you can see on my different simulation, it's more and more narrow with a number of blocks. Okay, so. And we have thousands of questions. What is the limit distribution? I think we are far from answering that. Far. What about the spreading? What about these kind of phase transitions? They are really typical. We can see them in every simulation. Christmas tree, oscillation, stabilization, and then, I don't know how to say in English, but turning around, and maybe something else later on. We don't know.
Is it possible to consider like a single node with a larger Hilbert space?
Yes, sure. Seen from, if you look at a block as a point with larger Hilbert space, you have an open quantum walk on the blocks.
So the question is now, what is the dynamics inside each of these?
Yeah, but they communicate. I mean, it's more complicated. We are really in a situation. Yes, Tony. No, nothing. We've spent hours with even very, very basic examples. And but that's what we get. So and we have this. I mean, I'm not the right person to make grand physical statements, but we have this impression to be in this situation where you have almost closed system, unitary evolution, which are connected very weakly to the others, and with time, this whole thing takes becomes kind of dissipative. Even for we have idea that, for example, we can use this thing, these models, to test, to make, for example, we never did it because also it's difficult to make a simulation, but we had an idea of, for example, doing this. So partitioning in blocks like this, so a set of blocks with random walks, and two big blocks at the end, like reservoirs. You put an initial state here and here, which are different, like that kind of Gibbs states, and let's go, let's evolve, and let's see what you obtain. So here you put the temperature, here you put another one. Let's go. It sounds interesting. Yet we never did it, so I give you the idea. I don't care. So here we are, and I think I'll stop here because I have not much to say about that.
So thanks for this very stimulating talk. There were already quite a few questions. Maybe we have time for a few other ones.
No, it's not a question as usual. As a mathematician, I've used to work with mathematicians. How did you accept to work on a subject which you don't have the demonstration of? You see what I mean?
Because I'm open mind.
No, really, it's a limitation when you work with mathematicians. They answer you, I'm sorry, but I know I won't get the answer, so ask someone else.
Okay, but what can I say? It's
So
okay with me anyway.
Don't worry, in 1 year you will have proofs.
So,
For the moment, it's okay with me, but we haven't written paper because.
as a poor physician, poor physicist, could you please tell us if there are physical implementations? Yes, in your that you know, there is one.
Of
there
open
are,
quantum walk, for example.
or any kind of walk. Unitary.
Unitary, I think, yes. I'm not the specialist in that, but there is a whole story of unitary quantum walk. I think there are implementations, like electrons captured on sides.
About the results related to what you with results related to what you said.
Which one?
Yeah.
Yeah, it is. Yes.
So yeah, you wanted to ask.
No, I don't say same question.
But with intermediate quantum walks, I don't know.
This
for
would be
example.
quantum transport. Yes.
What do you mean by quantum transport? Where is the transport?
For some
So another question is, what is the relation between your work and quantum information processing? Of course, because quantum walks have been discussed in this context.
From what I know, unitary quantum walks, they have been used in quantum algorithm because of their property to have high probability of presence far away at size n. So they have been very clever guys to use it to accelerate quantum algorithms. That's all what I know. Open quantum works will appear naturally in experiments or theories, like they have been doing. When you have repeated interaction and repeated measurements, you are more or less in a situation of open quantum works. That's all what I know.
No other question? Okay. So thanks a lot, Stéphane. And maybe say when Michel Bauer asked me to help him for building up the program, I have to say that I was a bit skeptical on this mixture of high-level mathematics and physics, but I have to say that it works. It really works well. This was a great idea. So thanks, Michel, and we can really thank him for organizing all that.
Again for everything he did.
So, if I may say one word of conclusion. First of all, this meeting was made possible because we had sponsors, so I should mention them at least once. So our sponsors were the CEA, the CNRS, the Agence Nationale de la Recherche, and in particular the ANR STOQ. Stock? Stock, okay. Stock. The Adamar Foundation in Mathematics, the Palm LabX, the Palm LabX, and what else? And also Michael and Victoria Berchatsky. And finally, so I wanted to thank all the speakers and all the participants for their efforts, because once again, I mean, I'm a bit disappointed, I have to say, that not so many people showed up to listen, but the lectures were of very high quality, and I wanted to thank you very warmly again for the job you did for this conference. Thank you very much.